Has everyone got the little pop-up?
No. Oh, yeah, all got that now. Great. Okay. So yeah, thank you all for coming today. So we have a talk for you today by Tony Maher, PhD student at Imperial College London, and it's the effects of weathering on the chalk unsaturated zone. Slide, there we go. So just a bit of housekeeping before we start. So we are obviously going to record the meeting today, and kind of any views expressed or anything in the Q&A session that might come up, that's solely the view of the individual, doesn't necessarily reflect the views of the ICE, the BGA, or the BGA ECG, just to kind of let you know that. I think we're all used to it now, but if you can stay muted kind of when the main presentation is on the go, that would be appreciated, kind of reducing some background noise. And if you've got any questions, Tony's happy, for those to come up during the talk if it's easier. So, raising a hand or kind of any questions in the chat box, that's fine. Or we've got, 5-10 minutes for a Q&A session at the end. And then there'll be some announcements from the early careers group, and then we'll close the session. So Tony's full title of the talk, I suppose, is The Effects of Chalk Weathering on the Hydrogeological and Mechanical Properties of the Chalk Unsaturated Zone. So I think it should be a good talk tonight. So I will stop presenting now, and then you can share your screen, Tony, if that's okay.
Yeah, no problem. Just 2 seconds.
Oh, no worries.
Okay, can everyone see that?
Yep, all good, yep.
Okay, just bear with me. I do want to just quickly switch my camera off because I'm using Wi-Fi and it may drop out. So I'll just briefly, while you can see my face, I'll give you a quick introduction to myself. My name's Tony Maher. I'm an engineering geologist at Imperial. I'm going into my 3rd year, and I'm basically working on chalk weathering. So just bear with me and I'll put this presentation on. Is that full screen for everyone yet?
Yeah, that's perfect. Thank you.
Cool. Just to throw out a few disclaimers. So I'm not going to talk about the entirety of my project. I'm just going to be talking about the test procedures and the field work that I've been undertaking. Another disclaimer: I am not a hydrogeologist. I'm looking at some of the hydrogeological properties of the chalk, but my main background is not hydrogeology. Just a bit about the project. It initially started out as a project sponsored by the nuclear guys at Imperial, and what we were trying to look at was whether or not weathered chalk would retard the movement of radionuclides into the underlying aquifer. Later on, it was identified that basically the medium of transmission or likely transmission would have been water in this sense. So therefore, the project basically moved into a water project. But then it's also the material properties which would be required to be studied first, basically. So that's just to give you a bit of a flavour of the original background of the project. So the contents that I'm going to work through the aims of the project. I'm going to show you a quick overview of the lithology of the area. An overview of my field work, the subsequent laboratory work, and then probably, well, not probably, I'm going to go through the future work of which I intend to do following on from these bits. So the motivation for the project: the UK chalk aquifer is quite significant in the UK. It's a principal aquifer. Well, the EA specify it as being a principal aquifer. We get a significant amount of possible drinking water from it, around about 20% of our total drinking water. And we're also going into a period of climate crisis where we're going to have periods where we have excess water, so we have flooding events. So that's going to have implications for our infrastructure. But then we're also going to have periods where demand is greater than we can actually access, where maybe these aquifers are a little bit less full than what we're normally used to. And that has implications for water resource management. And again, also water security is becoming a concern, because as this gets progressively, if this carries on getting progressively worse, then obviously these problems are going to get exacerbated with that. Okay, so on the left-hand side, sorry, I'll just put a pointer on. Give me a moment. On the left-hand side here, we've got basically the onshore deposits of chalk. It's it's quite significant. It covers around about 21,500 kilometres square. It extends from Dorset round to Norfolk on the actual coast, and it strikes inland roughly northeast to southwest. What this map doesn't show is that actually, it obviously extends under the ocean, under the sea as well, surrounding the UK. So what the implications of having such an area so large is the fact that there's going to be quite a significant number of infrastructure projects and construction projects being undertaken, and these could be anything from something as small scale as fitting services under roads, all the way up to bridge building, tunnel construction, you name it. These projects are going on. On the right hand side, we've got a stratigraphic column. So this is based on the law of superposition, where basically the oldest deposits are on the bottom, the youngest are on the top, and this is how they would have basically been laid upon with representative thicknesses. Had there been no erosion, and they were just piled on top of each other, layer cake style. On the left hand side, we've got the actual geological time stages, and then in the centre, this is the biostratigraphy, which basically we use to constrain the deposits and figure out which deposits belong to which on the basis of the content of fossils and other paleontological aspects. Presentation's been a bit laggy. Okay, so the aims and objectives of my project is to basically ascertain the degree and the extent of the weathering in chalk. This is not really well understood. So this is going to be undertaken with a combination of, bear with me a moment, fieldwork and observation initially. So going to go out, observe the chalk in the field and basically start making observations, start developing maps and models from first principles. The next thing is to ascertain what the material properties of weathered chalk are, and this is taking chalk from a fresh chalk right the way through to weathered chalk, and everything in between. So permeability, changes in permeability, porosity, strength, and in order to do that, there's very limited field testing that we can do. So we've got to validate that with laboratory testing. Then there's the material effectiveness to impede the transport of contaminants into the underlying aquifer. So while I mentioned before about it being for radionuclides, it also covers most contaminants which will be transported in water or which is a liquid. Again, this will be undertaken with fieldwork and observation and validation from laboratory testing. And then a little bit later on, we had considered about weathered chalk being used as an engineering material. So the term putty comes from basically a polishing powder, and like many years ago, it used to be mixed with linseed oil and used as a sealant around windows. Now, the main difference between that and the putty that you find in the field is the fact that the putty found in the field is disturbed chalk mixed with water, and the idea behind it is we were wondering whether or not that would have the same properties as what the window putty had, and it would basically provide some sort of dense impermeable liquid, but unfortunately that's not the case, I don't think it's going to be the case, but that's going to be figured out via laboratory testing. Okay, so the chalk unsaturated zone, what is this? So basically, people may know it as the Vados zone. Okay, it's got an average thickness of around about 35 to 40 meters, but it can be in excess of 100 meters thick, depending on topography. It's characterized with the chalk material matrix itself is water filled. However, discontinuities which can run right the way to below to the saturated zone, these are generally empty. Water transport in these particular areas is through diffusion, and it provides quite an important recharge mechanism. Going back to the fractures, these provide preferential quick recharge, but these properties of the chalk, which make it a reasonably good aquifer, also make it quite at risk to contamination, because if you've got pathways for recharge, that and it's quick recharge, that could actually allow quick contamination. Going back to the matrix again, if the liquid is transported through the matrix and it's not free draining, it takes quite some time to go through. That also means that if that matrix becomes contaminated, obviously it takes quite some time for that to come out. So the difference between the chalk unsaturated zone and the saturated zone, as I mentioned, these fractures are empty, but in the saturated zone, these are generally full because it's effectively below the water table. The good thing about having the unsaturated zone for my project is that it basically means that it constrains my area of study to 35 to 40 meters, to the upper 35 to 40 meters. Okay, so fieldwork. I've basically been working a lot down on the East Sussex coast. It's really good in the summer. It's not so good in the winter. It's quite windy down there in the winter, but obviously in the summer, you're on the beach, and it provides some really good locations where you've got stepped and ramped access, which goes from the top of the cliff right to the bottom, and that basically takes you through the varying stages of weathering, and from incompetent chalk at the top right the way down to really competent chalk at the bottom in some locations. I would recommend, if anyone ever wants to do any chalk logging or go and get an appreciation, I would recommend taking a walk down there. It's quite nice. So the fieldwork that I've been undertaking, while I've got the basis for observation is the Syria grades, C574. What normally has to happen is I will describe the rocks via the British Standards 5930. And then bring this Syria C574 Syria grades into it. So the grading comprises of three components. One is a classification of fracture spacing. So obviously, that's a quantitative. That's quantitative. Then you've got the classification of the fracture aperture, and then you've got an assessment of density. Now, when I initially started this project, I had to do an MRes, and part of it was to evaluate how suitable this Syria grading classification was for weathering, and initially one thing that we did identify was the fact that this particular aspect of it, the assessment of density, held quite a degree of subjectivity, because a couple of the tests were nail penetration or hammer pick penetration, which you couldn't really measure, you couldn't really repeat with confidence or with precision, largely because of changes in difference in physiology between engineers, and also experience as well. So in response to this, the methodology which I adapted was to apply a uniformity survey, and I used portable non-destructive testing equipment, which I'll go on to in a moment. So the Syria grading framework, on the left-hand side at the top here, this is the aperture, the aperture, and also the aperture spacing, and also in this sense the texture, what you can observe in the field, and then you've also got the actual discontinuity spacing. Now these are hydrogeologically, or in this sense hydrogeologically relevant, in the fact that these are the aspects which provide rapid recharge, conduits for water going into the ground. And then on the right hand side, so effectively these are chalk, structural chalk as opposed to chalk material. These will be rock mass properties, whereas this one on the right hand side is the actual density grades, which in an ideal world you'd be able to test in a lab, but in the field you've obviously got approximations. It was hoped with these non-destructive testing techniques I'd be able to undertake a bit more constrained testing in the actual field itself, and this basically relates to the actual material properties as opposed to the chalk mass. So the equipment that I've been using, on the left hand side is an OS 120, which is a pendulum hammer. The test surface on that is quite large, and it provides a rebound number based on elasticity. The Silverschmidt L-type hammer, which is this one in the middle, it's a concrete test hammer, but it's for low strength concrete. So if you're testing green concrete or anything which is not quite cured, and that provides 735 newtons per millimeter. And on the end of that, I mean, this is not the mushroom plunger, but there is a mushroom plunger which I've been using, which basically increases the surface area, so you're not punching into softer material, although it doesn't always work. And then this particular piece of equipment on the end is an Equitip Lieb hardness tester. This is the D-type. So this was initially developed for material testing of metals, but it's only provides an energy of 11 newtons per millimeter, and it's got a very small surface area for impact. So what you generally find is that you can test much softer materials with this. It's much more sensitive, and you don't really get any sort of loss of energy in things like fractures and stuff like that, because the surface area is much smaller. So these are basically so going back to Syria, these are basically what I've been using to basically inform this part of the framework of the Syria grading framework. So these are the locations that I'm on, that I've been working at, and generally I'll I will use a wooden quadrat, going back to my school biology days. So it's a wooden square with a load of pieces of string with a grid system in it, and basically I use that to place down onto the chalk, and it allows me some constraint to be able to test relative hardness changes across the actual chalk itself. So second one, so Rodine itself, Rodine is New Haven chalk, and then over in Portobello, this is also New Haven chalk, but in this particular area here, it crosscuts. Sorry, no, not that area. That area there, it crosscuts a weathered valley. The access point actually goes right the way through that sequence, so that's good. So you can actually see the changes in rock density as you move down. And then over in New Haven, this is Culver chalk. It's much softer, and you can tell between the results. I have done another couple of areas, but I'm not going to be presenting them in this particular talk because it'd be much too much. So ultimately, going back to the aims which I had, I'd be looking at figuring out what the density, what the extent and distribution of the chalk is going to be. And so from these field observations and ground truthing, the data is going to be fed into a 3D model, which has been developed over the past 12 months. And in this will help basically map out the extent of the chalk. These particular two curves, these are effectively meant to be these provide a weathering profile on the chalk. However, it doesn't accurately reflect what we see in the field. So a little bit more work is required for these. Basically, these two equations provide these two curves on top. This particular graph on the left-hand side is the coastal recession at Berlin Gap. So this was the yellowy line here was from 2008, and this one is from 2020. So in that 12-year period, we've lost, roughly around about 10 meters worth of chalk in profile, which in a 3D section is actually quite a significant amount. So going back to my field observations, this is again Rodine access point. If you ever go down there, it starts off at the top of the cliff, and it's a nice ramped access right the way down. This strikes east to west. On your southern side is the actual sea, and on your northern side is inland. What the idea behind this particular observation is that it allows you to basically, or it allows me to find macrostructures where there's likely to be weathering or there's likely to be weathering or water ingress, and it helps me to basically figure out what is actually going on with the ground. One thing that can be noticed here is the fact that there are a number of competing types of weathering. So in this area, we've got these cryotubation lobes here, which is product of ice churn and segregation due to ground freezing from the last ice age and periglacial action. And that's one particular type of weathering. Given its coastal location, there's likely to be some haloclasty in this area as well. With it being on a cliff and in the sunshine, there's going to be some wetting and drying action there, and then obviously there's physical abrasion from the wind as well. And you can really see that in the changes of texture. Without even quantifying it, you can see these changes as you go on. So the further down section in Rodine is this, and this is probably only about 20 meters away from the last picture. And what you can actually see in this is, again, macro textures which are going to have an impact. You've got horizontal and vertical foliations, which will likely change the flow regime. You've got steeply inclined conjugate fractures in this area, which normally they probably would provide conduits for water. However, these are actually infilled with flint in this area. You've also got marl seams as well, which with a change of density in these, then that will obviously change any sort of percolation of water down, provide a little bit more resistance in that sense. And then back over to the Portobello outfall post, you can see the significant difference. This is probably about, I don't know, 2-3 miles away from Rodine. So there's a significant difference in the chalk. You can see it from the colour. You can see it from the structures which are actually in there. I mean, this is a massive erosional bite taken out of the cliff here. There was a broken pipe, which I think has provided a weakening mechanism there. And if you look up in the top here, this is taken from Mortimer. This is a schematic of a weathered valley, and you can actually see that if you were to manage to get out onto the beach a little bit further out, you can see this weathered valley pattern in there. So looking at the actual section where I've done like a bit of a vertical column here, you can see that the grades basically move from DM chalk there are some patches of DC chalk, but mostly it's DM until you get to around about 18 meters above ordinary datum, 12 meters along the scan line, at which point the grade starts to pick up and you get a medium to high density chalk. And then as you move down, you're getting a much more competent chalk as you move down section. So the quadrats that I mentioned, which I knocked up in my bedroom, so these basically just allow a little bit of constraint on the ground. So rather than checking out like very small discrete points, these actually allow a 0.5 meter squared area to be considered. And what you can actually see is there is actually a bit of a textural change. So this was used with the low strength Schmidt hammer, so the L type Schmidt hammer, and we are actually getting grades, even though this wouldn't really be considered a competent rock. But we are getting some readings from that, and then just below that, which is at the bottom part of the cryoturbation lobe. Again, you're still getting this really wide spread. These weren't what I was expecting. I was expecting like a relatively even change in weathering, and that wasn't really the case. Sorry, this is the second one. As you can see, the zeros basically denote areas where there was no recovery from the instrument. Again, this wouldn't be considered a competent rock. This is basically a load of pieces of chalk which are hosted in a fine mass of soliflucted material. So this basic soil material, we're getting no readings from it, but these particular small discrete readings, they are reflective of the actual rock material as opposed to the rock mass, because obviously you can't test the other material surrounding it. But as we get into more competent material, you can actually see where these where the fractures and discontinuities start affecting the readings. So no longer is this a chalk hosted in a soil. This is becoming a bit more competent. Chalk clasts are becoming a little bit greater. You're probably talking brecciation type 2 here from Merton's papers. But again, on the bottom, we're getting significant numbers of no recovery there. So again, a bit more competent. So we're looking at like chalk is around about 90% of the observable material is competent chalk clasts. But again, it's around about C3. We've got quite a significant number of discontinuities in there, and again, that really reflects in the quadrats on the right hand side, the readings. And what that basically is where the energy is being lost via these discontinuities. Again, this is a really good example. And as we move on, and again, this just basically helps me evaluate the uniformity of the actual material as I'm testing in the field. It provides constraint. Sorry. So once I've finished my fieldwork, normally what I've been doing is I've been collecting samples, and what I've been doing is bringing them back to the lab and undertaking index testing. So for the index testing, we do natural moisture content, which is the amount of moisture which is found in the rocks in situ in their natural position. So take the rock, wrap it in tin foil, stick it in an airtight bag, bring it back, test it as soon as possible. Then we've got intact dry density, which is the actual material density of the rock. The saturated moisture content, which is the maximum amount of moisture that the chalk will hold. Uniaxial compressive strength, then slate durability, where basically it's the durability of the rock in response to cycles of wetting, abrasion, and then drying, and then the porosity values are estimated and then validated. But the most important value in this particular suite of tests, especially for weathering, is the intact dry density value, and I'll come on to that now. So back to our law of superposition. We've got the oldest rocks on the bottom, we've got the youngest rocks on the top. This is in sequence order, and what we've generally got is we've got a medium density. These are average values, so obviously some fall into the lower values and some fall into the higher values. What we generally tend to find is the younger rocks are less dense than the older rocks, which is likely to be in response to overburden consolidation, and some form of diagenesis. But the trend on this particular graph is quite important. So what we notice is largely they get the older they are, the more dense they are, with the exception of the Hollywell nodular chalk formation. Now, the Hollywell nodular chalk ties in with the KT boundary, which is associated with a significant amount of volcanism. So it's likely that there's quite a lot of bentonite in this particular formation, which makes it a little bit more nodular, a little bit more resistant, a little bit more hard. But when we then plot saturated moisture content against formation, we get the opposite trend. So what we have is the younger chalks, which are less dense, having a higher saturated moisture content, whereas the older chalks generally tend to have a much lower. Now, the reason for this is likely to be because, and this is what strengthens the consolidation and re-cementation of chalk, in the fact that this is likely due to occluded pore networks. So where we had like a high porosity in the chalk, the older and the more compacted it's become, these pore networks have some pores have closed, some have become a bit more tight. So there is a relationship between intact dry density and the saturated moisture content. So this graph was initially produced by Mortimer et al, and it's intact dry density versus saturated moisture content. Generally, chalks with a moisture content below a dry density below 1.7 generally tend to be the most active. These particular chalks can take on board water and lose water with much greater ease compared to the more dense chalks. Now, the implications of that, it's quite important. This is quite important because water is quite a significant weakening agent for chalk. So that means that chalks which can take on and drop water or take on board more water are likely to be more susceptible to weathering in that sense. So as we move on, we notice the same trend in the younger chalks. These have a much lower strength in terms of UCS. We don't have any UCS for the new pit in this sense, but we do have the nodular chalk, and again, this particular curve is pretty much the same with the same trends of the UCS. And on the right hand side, we've got permeability by formation, which basically permeability reduces with depth. With increase in age with the chalk. So why is density important, and is this geomechanical property hydrogeologically relevant? I think it is. I think that this is probably one of the key index tests that you need for estimating weathering and also susceptibility to weathering. Okay, so moisture content decreases with increasing dry density. Again, as I mentioned, because of pore space and occluded pore throats. So what that means is that the younger chalks are more likely to be susceptible to weathering. That said, the weakening process of the water weakening process will reduce the density of chalks. So even the tighter chalks, which have a low activity in terms of saturated moisture content, they will eventually become more weaker, and then they will become just as susceptible to weathering. Okay, so permeability decreases with formation age, and this basically reflects the ease at which fluid can diffuse. Because bear in mind, the water doesn't run through these; it actually diffuses depending upon its density. So to actually test the weathering, I have been undertaking artificial weathering, and I've gone back to using a slake durability machine. So the slake durability machine is 4 drums, which rotate a period of 20 rotations per minute. This is an automated unit, and basically these drums are half filled with water, and these 10-minute abrasion cycles are then followed. The samples are then taken out, and then they're placed into an oven at 105 degrees. And basically, this emulates wetting and drying cycles in the field, and also the abrasion. And what we actually see is some quite significant. So if you imagine that these have only really been in, abrasion for 40 minutes there. So these are culver chalk, so they are quite weak. But these are the broken up samples on the left-hand side, and as they get progressively more broken up and smaller. Now, this is not just an inherent material property. If there are any discontinuities in these fragments that we place in there, that is likely where you're going to get quite significant pieces of material loss. So you're going to get smaller fragments coming off, as opposed to a uniform wear down of grains coming off the chalk there. So coming back to we've got the very similar pattern. So we've got very, very dense materials having a higher durability to the slaking, and the younger, less dense materials obviously slake much more quickly, which effectively will give us an indication of the relative rates of weathering, you know, in the field, and it, you know, indicates durability, particularly if you're going to use chalk as an engineering material or anything like that. So in order to validate, in order to check out some other aspects of chalk weathering, there are certain weathering agents in chalk, such as salt for haloclasty, which you can't see with the naked eye, and you can't differentiate haloclasty from any other type of weathering. And we know that we know that chalk weathering basically changes the pore network. It changes the density. So if it changes the density, it likely changes the pore network within the chalk. So in order to observe this, I've been using a scanning electron microscope, the TM4000 tabletop SEM, which is compatible with an X-ray dispersive, an EDS machine, which basically allows identification and quantification of chemical elements within the actual chalk itself. Now, the challenges of using this particular technique is this picture on the left hand side. Without the EDS, it's quite limited. We're stuck with basically being able to identify grains and minerals on the basis of habit, you know, shape, any obvious signs. So in order to basically back that up, we need to use EDS to basically interpret the mineralogy. So from the EDS, this is quite interesting. So this is from Telscombe Cliffs. So this is Portobello at the base of the beach, and what we've got is these cubic minerals which are sitting within the ground mass. And from what you can actually see is these have nucleated within that particular ground mass. So when I've come to undertake the EDS analysis on it, I'm getting quite a significant amount of sodium and calcium values in there. So given that these particular the habit of these particular crystals is cubic, and the prevalent mineral in there or the prevalent element in there is sodium, you know, the likelihood is this is haloclasty. This is, you know, haloclasty weathering within that particular chalk, you know, that in combination with the location where the material was sampled from, that obviously gives an indication as to what, you know, we're actually looking at. So bear with me a moment. So this is just basically where I've undertaken a bit of interpretation. So we've got acicular grains here, which is likely to be reprecipitated calcium carbonate. We've got not the stereographic surface on these particular samples. It's not flat. It's not, you know, it's quite irregular. You have these breaks of slope. You have all these other minerals which are going on in there. Salt crystals, and then disaggregated coccoliths. What the hope is that identifying weathering, it's different stages of weathering in the field, we'll be able to basically go away with these particular weathered samples, place them in an SEM, and identify patterns within the chalk matrix. And from then it'd be hoped that we'd be able to come up with some sort of index where it's almost like a book. You can pick it up and you can say, okay, well, that is roughly a DM chalk or whatever, just from looking at the ground mass. So that's basically one of the validation methods that I've been using. So in conclusion, the field observations that I've been doing allows for the identification of areas of weathering for testing. So basically areas of interest, you know, you can see the changes in chalk grade, you know, in changes of colour, in changes of texture, you know, hardness in your hands. So the field observation is really important. Okay, there are numerous competing weathering processes which can be observed in the field, but they require laboratory validation. You know, you can't basically turn around unless you see landforms like cryotubated lobes and stuff like that. You couldn't tell what type of weathering is going on just from looking at the actual texture in the chalk. Okay, so weathering's not uniform across rock face areas. You get a lot of edge effects, discontinuity effects, and there is heterogeneity observed. These are basically what was observed in the quadrats as you know, in different values, in different changes of UCS. Okay, there's a significant relationship between intact identity and saturated moisture content, and this has got implications for weathering and even identification of weathering. Okay, lower intact identity chalk, sorry, that's wrong. Is likely to be less susceptible to weathering, whereas sorry, yeah, lower intact dry density is likely to be more susceptible to weathering, whereas high density chalks are likely to be more durable and also be less susceptible. Okay, and also high density chalks tend to have an increased durability when slaked, which would also indicate that in the field these are less likely to be weathered due to wetting and drying cycles as what a younger chalk is likely to be. Okay, so the future work in terms of lab testing, I'm going to continue with the SEM and index testing of the chalk, and that'll give me the material properties and the microtexture index. Going to subject samples to different preparations. So in order to model whether or not salt weathering makes chalk less durable, I'm going to probably follow along with synthetic groundwater and some salt saturation. Even to test the actual water weakening effect, I'll probably take the water out and maybe use something like glycol. So basically the chalk will then only be subject to the abrasion and the heat process. The problem also is that you require vacuum saturation over quite a significant period because the rate of diffusion of the water into the chalk will take quite some time, and then the drying period to ensure crystal nucleation for weakening agents such as salt in there. Hopefully undertake SEM and index testing prior to and after the slaking to see whether or not there's any difference between the two, and see whether or not the slaking process, rather than just being a mechanical process which removes material, whether or not it actually changes the material properties of the samples in the actual slake durability machine. Also, with the slake durability, there's quite a significant amount of horizons which come off, and there is a difference between the actual horizons in terms of grain size and whether or not there are any fragments in there, colour. So what I'm looking to do is to undertake some visual analysis and also use some particle size distribution on them. And again, undertake SEM and index testing on both the matrix and the horizons. And that is me. So if anyone's got any questions, I'm happily take them.
Great, thank you very much, Tony. That was really good. Really, that was information, not overload, but a lot to take in there, which was really nice. I guess I'll kind of kickstart kind of some questions then, just to give people a bit of time to think about if there's anything that they wanted to ask. One of my questions was, it's a bit of a general one, but you're in your third year now, has anything kind of really surprised you, any of your findings, either from some of the site walkovers or some of the lab work? Has anything really surprised you that results have come back that you weren't expecting, either for kind of good or bad?
That's a good question.
In line with kind of literature.
It generally does tend to follow the literature. What surprises me quite a lot about it is the fact that some of the things which you would think, oh, that is what I would expect to see in the literature, is not actually in the literature. It's not being actually observed or anything like that. So, or it's not being recorded. So like the durability, like I was surprised at that the trend of density increasing sure. with age. That was quite surprising, I thought. So
okay. There's one in the chat here. So did you find any rate effects when testing for UCS, given that the samples were unsaturated?
I don't know about rate effects. Some of the unsaturated, generally what the unsaturated samples tended to be, the unsaturated dried samples tend to be stronger than the salt saturated or the wet samples which were tested. That was one trend. So
okay. Charles?
Yeah, with your weathering mechanically in the lab, are you able to relate to time, or is it just relating sort of relative field observations to its stage of weathering?
I don't know yet. Now, I'll tell you a couple of things what my supervisor has asked me to do. My supervisor has asked me to test some samples until absolute destruction. So I've followed the guidelines for the slake durability, followed the standard on that, and I've placed them in. And I've tested the samples way beyond 5 cycles of 10 minutes, going up to the point of where you're talking hundreds of minutes. And what I've noticed is that the smaller the samples get, and I think that this is probably an interaction between the machine and the actual size of the samples, the smaller the samples get, the less amount of material is lost later on. So I think there's a size effect there with the machine. But no, I've not been able to relate anything, because the problem is while you're subjecting the chalk to heat and water and abrasion, it's not really a true analog of what's happening in the field. In terms of like wetting and drying cycles, or there's a lot more in the due to weather and stuff like that going on compared to what the actual slate durability. So while the slate durability is good, it's not a true analog.
Yeah. And does the baking it change the chemical properties at all, or is it not hot enough?
I don't think it's hot enough. I think I think it's around about 400 degrees where before chalk starts getting denated. That said, though, I mean, I'm sure that progressive heating will actually change it at some point. What I have noticed as well is I think that there's quite a significant amount of the water weakening effect there, in the sense that if the water's not changed, you generally tend to, and it's saturated with calcium carbonate, you generally tend to not lose quite so much material in any one go. And so I think you just reliant on the abrasive action then.
Okay, thank you.
Okay, any other questions coming in, or no? Oh, we have a hand. Rich?
Hi there. Hi. Yeah, it's Rich speaking here. Formulate a decent way of putting the question, but since I haven't managed to do that yet, I'll ask anyway. We're using Syria 574 in industry with chalk. Me personally, when you're working on a project and you don't have much data and you're writing at the front end, and it gives you some guidance around various parameters, such as the intact dry density, which is a very, very broad range. And then it gives you some parameters around angular friction as well, so more on the strength side than perhaps what you've been discussing today. And I believe off memory it's a 31 to 34 friction angle, so that's a very, very tight range for all gradings of chalk. What relevance do you see of C574 today in industry? Do you feel there's a need for this to be updated?
I wouldn't say updated per se. I mean, because I don't know if you know the history of C574. So initially, the chalk grading started out. They were produced the Munford grades. They were produced by John Bell and a few others for a site in Munford in Norfolk. And then they changed to another set of gradings, and then eventually they got to this particular one. And it was made. These were mainly developed as a supplement for 5930. I don't think that they need revising so much to the point where we're not looking. I think that maybe some of the values need to be changed within it, and I think that maybe some of the tests, such as like the density tests, if we could find a density test which could be done in the field, which was repeatable and precise, that would be great. But I think at the moment, going off what the industry standard is, it's probably the best we've got, unless you can adapt it yourself to provide some sort of quantifiable data in that sense.
I think you've hit the nail on the head, Tony, there with regards to finding a mechanism to measure intact dry density in chalk, since the inherent properties of the chalk are based quite largely on this value and the relationship which it has to, say, saturated moisture content as well. And of course, not many. I mean, you can take the lab test, but typically you're not going to be specifying intact dry density for soils. If you know there's chalk, you can target it, but there's many times you're working in chalk and there's no data available on that. And then it's a case of you've got a huge range, and it's tough to work with what you've got.
Yeah. I mean, there's a certain amount of. I mean, that's geology and geotechnics for you, isn't it? There's a certain amount of uncertainty with a lot of things, and that, with uncertainty comes risk. And I think that for things like chalk and stuff like that, the gold star premier ideal thing is to take it to the lab, but you're never always gonna have that, and I think this is where the problem comes down to between engineers is having experience. So my experience is probably different to Emily's experience, probably different to your experience. So between the three of us, if we were trying to discuss something, things could get lost in translation there in that sense.
Great, thanks.
Okay. Great stuff.
Charles?
Following on from that, how have you handled sort of the disparity between observations and behavior in the field, and then sort of the behavior you're seeing in the lab with sort of, if you have different levels of weathering you're observing, do you have to take larger samples to make it representative in the lab?
That's a good question. It's quite tricky trying to take representative samples in the field to bring back to the lab, because you know, chalk is notoriously difficult to sample using mechanical means. If you were to try and take as undisturbed as possible a sample of DM or DC chalk, but by virtue of taking it out of the ground, you end up disturbing it anyway. So it's best to obviously undertake your field testing as an approximation, and if you can bring it back to the lab, then test it. Yeah, I mean, there is obviously always going to be a difference there, because, you know, just by your own sort of judgment, you know, if you're using a hammer pick, you know, and hitting the chalk and then measuring how deep it's gone in, you know, and then you take that chalk away, there will be a disparity between the two, unless you are an absolute chalk ninja, if there is such a thing.
What a phrase!
Certainly not me.
Not just yet. Oh, great. Okay. I think I'll kind of call time on the questions there, unless there's kind of any final thoughts from anyone. Okay, great. So thank you again, Tony, for presenting that. Really, really great to have you update us today. Oh, I'm just trying to multitask. There we go, multi-fail.
I'll stop the recording.
Oh, thank you. I'm going to share my screen just very quickly.